Alright, now we're going to do problem number 2 of homework number 10. Problem number 2 is similar to problem number 1 of this homework, in that it involves several definitions. As we can read above, basically we use the lecture notes for the stochastic process to define the properties of different stochastic processes, explain the understanding of these properties in various ways. We have 8 definitions, 7 of which are required, but we'll go through all 8. And we're just going to run through them quickly. All right, the different terms that we're going to be, some of them are familiar, some of them are a little more obscure, but we're going to go through wide set stationary, or WSS. We're going to go through independent increment process. We're going to go through Markov processes. Then we're going to go through normal process, strict stationary process, white noise, which we mentioned in problem number 1. And then we're going to talk about mean ergodic process, and then we're going to talk about martingales quite briefly. All right, so let's discuss wide set stationary. We've talked about in previous homework assignments. Basically, it's defined by a process such that the mean is a constant, and the autocorrelation term is a function of a time difference. If we actually have these two, we can call a given stochastic process wide set stationary. Now, notice how we only use mean and autocorrelations is all we need to actually define WSS. Let's see if there's anything else we need to do. Based on this, we can do many things already. We can do state estimation, parameter estimations, predictions. If we know wide set stationary, we can basically do a lot of comparisons with mean square within mean square sense. We've done this in previous homeworks, as I keep mentioning. Most times we're not really worried about the specific, like for instance, for the mean, like what the constant's going to be. We don't really care. We just want to actually have this property so we can employ it. We pay attention more to the power of it. That's basically it for wide set stationary in a nutshell. Independent increment process, we talk about this because it's important for Markov. Basically, it's defined such that independent increment process basically means if we have a stochastic process such that at 2 time points t1 and t2, the difference between the difference in value of the stochastic process is that those 2 time points versus the difference of the stochastic process at 2 different time points t3, t4. Basically, given that the actual time intervals are not overlapping, if we know it's independent increment process, we know non-overlapping time intervals, we know that these two terms right here are also independent of one another. We actually have seen that before. We can apply this term. We've seen it in Poisson process. We saw it in random walk. We see it in Wiener, mispronunciation. Like I say here, it's important for Markov, which we'll discuss later. Okay. All right, so basically for Markov process, we say a process is Markov if the past basically has no influence on the future when the present is known. So it's a process that's basically defined only by present terminology. It actually kind of applies to various terms. I mean, we can call Poisson process, Poisson impulses. We can talk about both the semi-random and random telegraph, the random walk. Everything we talked about in the previous problem of this homework can be considered as a Markov process. A lot of things have Markov processes. In fact, we can actually Markov processes are widely used. Here we just briefly mention sometimes what the Markov chain. Now, normal process is basically when we have a stochastic process where the random variables with different time points are jointly normal for any n value, any time point, at any given time point, which we can define according to this chain right here. The statistics of a normal process is completely determined by the mean and autocorrelation. That makes it similar to our wide set stationary. It's just defined a little bit differently. The one big difference is that our mean is a function of t, while wide set stationary, we're working with a constant. Now, for our 5th term, which is strict sense stationary, a process is said to be strict sense stationary, or triple S, if its statistics are not affected by a shift in time. And we can see how this is defined here, basically. If we have an actual process, let's say, which is defined by a variety of different x terms, different time points, basically what we're saying at the exact same x terms, if we just make an incremental, uniform incremental change to each of the time points affiliated with each of the x points, it's not going to make a difference. These two terms are going to be equal to each other. The one thing about triple S is that apparently it's very difficult to actually meet this requirement and define a stochastic process as triple S. White noise we actually discussed before. We talk about here in terms of a Wiener process, the way I actually read it up. So we talk about it right here as, let me just go through this. Basically, we define it as a differential equation. We define it as a derivative. All right. We basically define it as a derivative of Wiener process right here. Gaussian white noise we defined earlier is basically, it's going to be the Poisson minus its mean. We talked about a little bit earlier. Let's see. A stochastic process is said to be white noise. It's basically the estimated value of the actual stochastic process is 0, and if we can define this as autocorrelation. Mean mispronunciation. Mean ergodic process. All right. If basically a stochastic process can be defined as mean ergodic, if I'm going to zoom in on that a little bit, if this right here actually is true. So basically, I'm going to take the time to read this out. If the limit of some time interval approaches infinity for 1 over 2t over the entire integral from the negative of this t term to the positive of this t term of this stochastic process, okay, if all this limit of this integral actually equals the estimated mean value of the stochastic process, then it is seen to be mean ergodic. That actually becomes important for problem 3 of this homework, which we won't talk about here in recording. Let's see. So basically, this applies within a mean sense square. That's about it. Martingales was the last one, quickly optional. Basically, it's a stochastic process is said to be martingales if the conditional mean equals the conditional. So basically, if we have a conditional mean right here, it's going to actually and this conditional mean right here is equal to, say, x1. The estimated mean value of this conditional can't talk. This conditional mean will equal the condition. So x1, x1. All right. This property is actually true for random walks in the Wiener process. So ends problem number 2 of homework 10.